Thanks for the introduction. I'm going to present you the work of our team about EMT, electromagnetic trackers, and in particular demodulation methods for your wireless system. This work has been performed in the Sysnav company in collaboration with GIPSA-lab and IEEE. So first I will make a brief introduction of electromagnetic trackers. Then I will introduce the wireless issue and the tracking methods that are usually used to solve it. And finally, we'll introduce the new method we propose to remove the initialization stage that is required for the tracking method. So what is an EMT? An EMT is basically made of transmitters that produce magnetic fields, which are measured by a sensor, which is localized by inversion of the major fields. The idea is to localize the sensor, so it's a 6-degree of freedom localization system, 3 orientation degree and 3 position degree. And it's a short-range system, most of the time around 2 meters max, but it has a very high accuracy, around 0.5 millimeter and 5 milliradian at 1 meter from the max error. The application of this technology are at first head trackers, which has been developed a long time ago for helmets. So the first patent is from 1979, but it's in development. There has been also a stronger community in medical devices using this electromagnetic tracker. And nowadays, this technology are developed almost for virtual reality device and augmented reality. I quoted here a patent of Ascension from Asher and this paper of Meier that developed glasses for virtual reality. I have also to mention some general purpose localization devices, which are sold as an alternative to motion capture. Which it has the same constraint actually of a range, but it removes the need of a line of sight. So we can quote, for instance, the G4 of polymers and spectrums. So the principle is the following. The transmitter is made of 3 orthogonal coils, which are powered at 3 different frequencies. Each coil is going to generate a magnetic field, which is mainly at first order the magnetic field of a dipole, which is oriented by an axis of the transmitter frame. On the sensor side, we will have also 3 orthogonal coils, and we are going to measure the voltage induced in each coil by the varying magnetic field, according to the Faraday's law. Then this voltage is amplified and numerized by an IDC and collected on the sensor board. Then we can do some processing, and the first step is a demodulation step, which consists in identifying in the voltage of each sensor coil the contribution of each frequency. So, for instance, the first coil you can decompose it as a sum of a cosine of the 3 frequencies, and we are going to retrieve in demodulation this capital U here. It's a signed information, sorry, because of the phase here has been set arbitrary to 0. Once this contribution retrieved, we can build a matrix that we call a magnetic matrix, in which the columns gather the information of each frequency, and the lines are the information of each sensor coil. And the fact is that there is a direct relation in theory between the pose of the system, so its orientation and position, and the magnetic matrix. So from the magnetic matrix, we can compute easily the position and orientation. You can refer, for instance, to this paper of Mr. Meier. So now, what is the wireless issue in this, and what are the tracking methods? So the motivation is the following. We want to impose a physical separation between the transmitter board and the sensor board, because for many applications, it's much easier to build a system usable. In practice, the sensor board or the transmitter board must be really small to be embeddable. The problem doing so is that we have now 2 independent clocks with 2 different quarks that drift randomly from each other. So on the sensor side, we have a signal, and we know a theoretical frequency. So we can retrieve only the amplitude of the signal and the phase, but the modulo pi, not the pi. So to see what's the impact, let's make a step back, and I will present you this minimal example just to give you an idea. In this example, the transmitter is made of just 1 loop, a single loop, and the sensor is made also a single loop. The magnetic field generated by the transmitter is just the field of a dipole. And we are going to consider 2 degree freedom only, which is the position on the z-axis of the sensor, and the orientation, which can have only 2 states, either along plus z or minus d. So you can see immediately that measuring the derivative of b, you can retrieve the z coordinate. And the orientation of the sensor is going to be given by the phase. If this orientation corresponds to a signal in phase, a signal of a phase of pi will correspond to this orientation, to the other orientation. So what we lose when we are in a wireless system is the phase orientation. So in this trivial example, it's the orientation of the sensor. And we have the same problem actually on a 6-dimensional wireless EMT. But in that case, in our matrix, we will have an uncertainty on the sign of each column. And there is therefore 4 candidates for the magnetic matrix once we have eliminated the absurd one. And the tracking issue is to identify which among these candidates is the right one. The usual solution implemented are, so it's a patent from Pauline of 2008, are tracking methods. The idea is to place the sensor at an initialization position, which is known. At this position, we know the expected magnetic matrix, so we know we can retrieve the phase, and then during all the acquisition, we're going to track the evolution of this phase. We can also perform pose tracking. So we know the unit position. We perform demodulation on and extraction on the 4 matrix candidates, and we keep the one the closest to the unit position, and then we track it along the trajectory. The problem is that this initialization stage is not very practical for the user and must be performed each time the signal is lost. So we try to develop a solution that removes this stage. The idea is the following. We have 6 degrees of freedom, but we have 9 data in our matrix. So can we use the redundancy of the information to discriminate between the candidates? The short answer is no, we cannot, because without changing anything, because each candidate matches exactly the magnetic matrix of a pose. Said otherwise, each candidate is a perfectly valid magnetic matrix. So we cannot discriminate between them like this. So we have to break the symmetry, and that's what proposed in the presented paper. The idea is to break the orthogonality between the axes of the transmitter, so at an angle, in order to add non-orthogonalities. And we are going to calibrate this non-orthogonality, and then we are going to correct the impact of the orthogonality on, to apply the correction of the impact of the non-orthogonality on the 4 candidate matrices. And what we hope is that the only matrices, corrected matrices, of which will be valid magnetic matrices, will be the right one, and the other one will not be valid matrices. So what valid means actually to evaluate if a matrix is a magnetic matrix or not, we apply a criterion such as this one, which is just a relationship between the singular value of the matrix. So what's interesting is that we can prove theoretically that this method works almost everywhere except along 4 rays in space per wrong matrix. We can compute analytically the position of these rays. And I plotted in simulation, I retraced, sorry, this results in simulation. So you can see here the plots are the zone on the sphere where our method cannot be applied by interior. So in each of these plots, there is 2 candidates which have the same criterion, so which are perfectly valid magnetic matrices. And the zone is bigger. It is defined from a threshold, which is arbitrary. And the idea will be to increase the non-orthogonality in order to reduce this zone. And that has been, this dimensioning of non-orthogonalities has been also performed in simulation. Finally, we implemented this solution in a real system. So we made an EMT, a wireless EMT, and we implemented a phase tracking within the initialization stage to have a reference position, and then compared to the solution with the non-orthogonality method. The fact is that it works for a smooth trajectory almost everywhere as expected, with non-molecularly added defects. So we just used an orthogonal system, which is not orthogonal in fact. We calibrated the non-orthogonalities and used this correction, and that was enough in free space to find the valid matrix. So how we are going to use this? It will be actually to perform initialization in the tracking system, because what we show there is that when there is no stronger rotation, actually the wrong points here are the points of a sharp change of orientation. So when you don't move too fast, the method is always valid. And we're going to use this to perform the initialization of the tracking, which is a robust solution on the indeterminate rates. So as a conclusion, we propose a new method for the sound resolution during demodulation signals of wireless MT. It has the main advantage of removing the initialization stage and to keep analytic formulas. So that's for comparison with the error solution. And the use of our technology will be to reinitialize the tracking after a loss of signal, for instance, to make this simpler to the user. And our current work in progress is to make a prototype with the willingly added non-orthogonalities work, because it comes with a few issues. I thank you for your attention.